Hello guys, Mati here. It's been a while, and in our last episode we saw how we can add a REST endpoint to our Kafka Streams application so that we can query the state. And now in this episode, we want to add a second instance to our application so that we can see how Kafka Streams scales stateful applications. In this case, we want to see how the data is going to be distributed across the different applications, the different instances, and then we want to see what happens when we take one instance down and how the data is rebalanced once again. So welcome to Programming with Mati. Okay, so why do we want to scale? When the amount of data that our Kafka Streams application has to process grows, we might need some more computing power so that we can keep up with the desired time of processing. That's why Kafka Streams is built to be able to scale horizontally. This means that we can add more instances of our application so that we can increase our performance. What happens when the data is stored locally in the state store? So Kafka Streams uses a special Kafka topic to rebalance the application state so that the keys are distributed across the new horizontal structure. All state stores are updated to reflect the new horizontal structure. So let's see what happens when we add one more instance of our bank balance application. This is the current state of the application. We have the topic bank transactions, where we get all the transactions into the application, right? And this topic has three partitions, but the three partitions are assigned to the one consumer that we have, which is our application. So everything in the three topics goes into our local state store in the instance one. So let's say we have three transactions, transaction 1, 2, and 3, and each went to a different partition, partition 1, 2, and 3. The three of them ended up in our local state store because we only have one consumer for the three partitions that we have in our topic. Another thing that Kafka does is it will back up everything that we have in our local state store into a special topic which we have called bank balance store log. This bank balance store log is going to hold all the data that the local store has as well, so that it can be rebalanced when we add a second instance. So when we add a second instance, the two instances of the application will be part of something that in Kafka is called a consumer group. And this happens because both instances of the application have the same application ID. So the application ID becomes the group ID. This means that the three partitions will be shared across this consumer group. So two of the partitions will be assigned to one of the instances, and the remaining one is going to be assigned to the other instance. For example, if transaction 1 went through partition 1 and transaction 2 was going through partition 2, these two will end up in this state store. But transaction 3, which went through partition 3, is going to end up in the instance 2 store. What Kafka guarantees is that all the messages that have the same key will end up in the same partition in order. And because our bank balance ID is the key for our topic, every transaction for the same balance is going to go into the same partition. So we won't end up with transactions in different instances for the same balance. So this is a good thing. So now, how do we query a state store that is distributed? Let's take a look at the first diagram. So in the first one, we see a client accessing a balance which is found in the instance 1. So since the instance 1 is the one that received the call, the instance will resolve the call in itself. It will access the local store, get the balance 1, and return it. Now, in the second diagram, we can see that the client is trying to look for a balance which is not found in the instance that received the call. So in this case, the instance will ask Kafka in which host is bank balance 3 found, and Kafka will tell that the balance is found in instance 2. So the instance 1 is going to call instance 2, get the balance 3, and finally return it to the client. Why is the data distributed in our application? Kafka Streams distributes the data so that the queries and updates are faster to execute.
If we have less data, we can get results way faster than if we had to query a big store. But it also provides a different type of table called global K table, which is replicated across all instances. This means that all instances have the same data. We mostly use this kind of table for data that we don't expect to be updated as often, or we don't expect for it to grow that much. Because as you can expect, when you have a lot of instances, keeping all the instances in sync is a very costly process. We have to replicate and we have to stop processing while doing the replication so that we don't have errors in our application. In our bank balance application, we could implement at some point a global K table for storing the type of bank account. For example, we can have investment account, we can have savings account, current account, credit account. So these are the types of accounts that clients can have. And this kind of data is not updated as often. Maybe a new product is launched and we have to add a new row in this table. But usually this data doesn't grow that much and it's not updated as often. As always, you can find the code and the links in the description of this video, and smash the like button so that we can spread the word and get more people into the channel. And leave a comment. I've been reading all your comments and I'm getting a lot of feedback from you, so it's really appreciated, and keep it coming. Thank you for the support. Now, if you downloaded the GitHub repository, you have to step on this branch called Add Second Instance, because in here we have all the code that we'll need for adding this second instance to our application. So make sure that you are on the right branch so you can follow the tutorial. If you've been with us in our last tutorial, we created the bank balance service, which we are using to query the bank balances. And the difference now in this branch is that I created a new class called the bank balance repository. And this class, bank balance repository, is a class that will help us. So let's see what we have. First, we see that bank balance repository extends a generic Kafka Streams repository. So let's take a look. This is also a class that I created. And this class has different methods that we are going to use to query the data. Let's see what we have. We have a method called find and it receives a key. Okay. And we are going to use the query metadata for key. And this is going to return something called key query metadata. This is the kind of object that it returns. From this metadata, we can find something called active host, which has a host info object. So what we do here is if the host info is equals to the active host, then find locally. So what are we saying here? So basically what this means is that we're asking if the key is found in this instance or if we should query a remote instance. So that's why we have find locally or find remotely. If the key is found in this instance, we find locally. Else, we have to go remotely to a different host. So that's why we send the host information. In this case, we are finding locally, and in the find locally, we just say, okay, find the object for this key, or else just throw an object not found exception, and that's it. And the other thing that we need to do is we have to look for the find remotely. And in this case, the find remotely is an abstract method that we have implemented in our bank balance repository. So let's take a look. In the find remotely, we're going to use an HTTP client so that we can query the balance in a remote instance. So the instance is going to send an HTTP request to the instance that has the balance. So we're going to send a GET request as we did in the last video, but instead from the browser, we are going to send it from this instance. And we build the HTTP client. This library we're using, OK HTTP client, is a very basic HTTP library, which is very recommended. And so we build a request object. In the request, we send the parameters, which are the URL, and the parameters, which are the key of the bank balance. And so we send the request, and finally, with an object mapper, a Jackson object mapper, we are going to transform this request into a Java object, a bank balance. If there was any issues, we just throw an exception and that's it. So to sum up, in our generic Kafka Streams repository, we have a find method, which basically checks where the data is. If the data is in this host, then it will find locally, as we did in our last video. If the data is in a remote host, then we go remotely. And this is the main change that we did in our bank balance service. Now, I'm going to run everything into a Docker network. So that's why I created a Dockerfile, and I'm going to create a Docker image of our application so that we can replicate this image into multiple containers, and we can emulate being in a network with multiple containers running and calling each other. I don't want to spend a lot of time explaining what this does, but basically in the first bit we are compiling the application, and in the second bit we are building the final image for our application. Once this is compiled by Docker, we will have one image for our application. And then I also added a Docker Compose file. In the Docker Compose file, we have all our services. So we will have Zookeeper, we will have Kafka, and we will have the service to create the Kafka topics. And finally, we will have our two applications, Spring App 1 and Spring App 2. So Spring App 1 will have the image of our bank balance application, and the Spring App 2 also has the same image. We're mapping the port of one of the instances on the 7070 port on our local host, and we are mapping the second one on a 8080. Also here we can see the mapping of the volumes of our applications, and here we're saying we're going to set the host info property as Spring App 1, and in this case it's going to be Spring App 2. This has to match with the name of the container, because this is the name of the container in the network. Sorry, not the name of the container, the host name. So this has to match with the host info, because this is the name in the Docker network. Okay, so now we can go and build our Docker image. So if we go to a Dockerfile, in IntelliJ Ultimate Edition, you can run a Dockerfile from here. I have already run this, so if I go to the configurations, you can see I have an image tag for this Dockerfile. So this is the name of the image that I'll build. So I just need to do this, and I'm going to build a new image. This process can take a while because he has to download all the dependencies from Maven, and then it will build the image. Okay, so it finished compiling the image for our application here. So now I can use this image in my Docker Compose file, as I already did. Also, if you don't have IntelliJ Ultimate Edition, you can just go to a terminal and just type docker build -t for the tag name, bank transactions, and dot. So we're indicating that this is the directory where we have the Docker file. We're not going to do this now because we already did it with IntelliJ, but that's just if you don't have the Ultimate Edition, which I highly recommend you get because it's a very, very useful tool. Okay, so now we can run our Docker Compose file. We can run it also from IntelliJ, or we can run it just using this command on the command line. We're just waiting for everything to be created. Okay, both applications have started now. We have Spring App 1 and 2, and everything looks fine. So now we're going to run the bank transaction producer that we built for a previous tutorial. And see what happens. Okay, the producer just run, so we should have data in our databases. Let's see. So let's query it from the browser. Let's get bank balance 1. And we see here in the 8080, and we can also get it from 7070. Let's try balance 2. Here we have data, and let's try it from the 8080 as well. And let's take a look at the logs of our application to see where is this data coming from. Is it getting it locally? Is it getting it remotely? So let's take a look in the logs of our application here. So we see looking for object with key 1 locally, looking for object with key 1 locally, looking for object with key 2 locally, and Spring App 2 finding bank balance key 1 remotely and key 2 remotely in host. All right, bank balance 1 and 2 are in host Spring App 1. So let's see if we can find one bank balance which is not in the instance 1. Let's try 3. Okay, so 3. All right, so 3 is found locally in a Spring App 2. So now if we change this to 7070 and we query it, we should have found this remotely here, right? So bank balance 3 is remotely found from Spring App 1, and it went to look for it in Spring App 2. So this is great. Now what happens when we take down Spring App 2? Let's stop this container. Okay, we have stopped this. So now, where is bank balance 3? Let's see what happens when we query bank balance 2 is still there. And now what happens when we query bank balance 3? It's still there. So now what we see is that even bank balance 3 is found locally in Spring App 1. So what happened is that the load of data was rebalanced across all the instances. So since we now have only one instance, Spring App 1 has all the data now. If we restart Spring App 2, let's start it again, and let's see how the data is redistributed now. Okay, so let's go with bank balance 1, and in here, since bank balance 1 is still in Spring App 2, let's see what happens with bank balance 3. So bank balance 3 is not found in Spring App 1, so it got rebalanced back into Spring App 2, and this is awesome. This is what we expect, and this is all taken care by Kafka Streams automatically. You don't have to do anything. The application gets rebalanced. You just need to tell Kafka Streams the information about all the different hosts, and Kafka Streams will store this information in Kafka and do the rebalancing under the hood.
Alright guys, so that was all for today. We saw how we can scale our application. We saw what happens when we take down one instance of the application, how the data got rebalanced into the single instance that we had, how it got rebalanced again when we started the second instance. I hope this was useful for you, and I want to thank you all for your support. It's been really great. I can say now that we have 300 subscribers. So I'm very happy with that, and I want you to know that I have a lot of videos planned for this channel. In the next videos we're going to learn about error handling, about windowing, and more advanced stateful operations like joins. So I'll be waiting for all of you in the next video, and as always, smash the like button, comment, subscribe, tell your friends, and keep all the comments coming. Thank you.